Modern factories operate at speeds that blur human vision. Thousands of motors, valves, and actuators fire in exact synchronization, building complex machines in seconds. Look at the exact alignment of these glass bottles on this conveyor belt. A fraction of a second delay in filling, and glass shatters, liquid spills, and the entire production line halts. Here, white robotic arms perfectly synchronize to assemble heavy battery components. Every joint rotates and every gripper clamps with micrometer precision. Behind all this chaotic motion sits a single, invisible decision maker, coordinating every microsecond. To understand how it orchestrates this industrial ballet, we have to look back to a time when factories actually thought with massive walls of moving metal. In the mid-20th century, automation was completely analog. We see it here in this vintage green control room, where technicians manually monitored massive banks of gauges and dials. To automate a simple machine back then, engineers relied on physical electricity to make decisions. They used a device called a relay. When current runs through a copper coil, it generates a magnetic field. That magnetic field physically pulls a metal lever across a gap, closing a circuit. If you wanted to create a safety rule, say a motor can only start if a door is closed, a guard is down, and a button is pressed, you had to chain multiple relays together. Current had to successfully travel through all three physical metal gates to turn on the motor. This physical wiring and heavy rotary switches worked, but they were fragile. Every decision point required an actual moving mechanical part. As factories scaled up, the logic required to run them grew exponentially. Facilities built massive cabinets, entire rooms, dedicated to holding thousands of these clicking blocks. By the late 1960s, this system reached its absolute physical limit at places like this General Motors assembly plant. GM introduced new car models every single year. Updating the factory floor meant electricians had to spend weeks manually tearing out and rewiring kilometers of copper wire. If a single relay jammed or one wire frayed, the entire line stopped. Finding the specific point of failure among 10,000 identical metal boxes meant losing millions of dollars in production time. As long as factory logic was trapped inside hardwired metal cabinets, manufacturing could not scale any further. General Motors issued a challenge to the engineering world: build a solid-state replacement for the mechanical relay. An engineer named Richard Morley answered that call with the Modicon 084. It was the first Programmable Logic Controller, or PLC. Morley's team had a digital microchip capable of doing the math, but they faced a massive human problem. The electricians who kept the factories running didn't know how to write computer code. If the interface looked like a text-based programming language, the factory floor would completely reject it. Instead of learning code, electricians got a visual interface mimicking wiring blueprints, ladder logic. A physical coil became a digital circle. A switch became a bracket. When conditions are met, the symbol turns green, simulating real electricity. By speaking the visual language of the workers, the PLC bypassed decades of resistance. A massive, room-sized wall of hardwired iron was instantly compressed into a flexible, easily reprogrammable line of software. PLCs rely on a continuous digital loop, the scan cycle. Step 1 reads inputs, storing sensor states. Step 2 executes logic, comparing data against the rules. Step 3 updates outputs, sending signals to spin motors. Then it instantly starts over. This tiny silicone chip repeats the read, execute, write loop millions of times per second. To the machinery, it feels instantaneous. Because the entire sequence happens inside a microprocessor, reconfiguring a massive production line now required typing a few keystrokes, eliminating the need for wire strippers. Today, our laptops and smartphones have processors millions of times more powerful than early PLCs. Yet, if you walk into any heavy industrial facility right now, you won't see consumer operating systems running the robots. Consumer computers process tasks unpredictably. If your laptop decides to run a background update, your mouse might lag for 1/10 of a second. In a factory, a 1/10 of a second delay means a hydraulic press crushes a piece of equipment. PLCs operate on determinism. They guarantee a response in an exact, rigid time frame every single time. Furthermore, industrial environments are brutally harsh. A standard motherboard would corrode or warp under the intense heat, constant physical vibration, and heavy electromagnetic interference generated by arc welders and giant motors. PLCs are armored, designed specifically to absorb this abuse and keep scanning without dropping a single bit of data. A desktop computer is designed to juggle thousands of random, complex requests adequately. A PLC is engineered to execute one precise loop with absolutely zero margin for physical error. Since the Modicon 084, PLCs have quietly absorbed every major technological leap. They evolved to communicate across global networks, integrate with massive data servers, and coordinate the industrial Internet of Things. Every bottle of water you drink, every car you drive, every package delivered to your door passes through a physical system controlled by this exact digital architecture. Behind the sparks, the roaring motors, and the sprawling assembly lines, a small armored box sits quietly in a cabinet, executing its logic millions of times per second, building the modern world.